Welcome to my talk about the investigation into the sources of side channel leakage that stem from the parasitic components found in the masked circuit layouts. My name is Danilo Šijačić. I am a PhD student at KU Leuven in the COSIC research group, and this is joint work with Josep Balasch and Professor Ingrid Verbauwhede. Before we start, let us specify what do we exactly mean when we talk about the side channel leakage. Prior to side channel analysis, cryptanalysis was the main method of attacking cryptographic algorithms. Namely, for a keyed algorithm, such as, for example, AES, an attacker would have to feed the data into the algorithm, collect the outputs, and then try to perform cryptanalysis to recover the secret key. Cryptanalysis targets algorithms, and it works independent of the implementation. On the other hand, side channel analysis targets specific implementations. Given a cryptanalytically secure function f, such as the modern AES, once we fix an implementation and start measuring physical emanations of the target device, side channel analysis can be used to recover the secret key based on the information embedded in these physical channels. These channels include, for example, execution timing or electromagnetic emanation or power consumption. The one we focus on is the power consumption, or more precisely the supply current of the device. Henceforth, when we mention the side channel leakage, we talk about the information about a secret key embedded in the supply current of the device. Predominant countermeasure against side channel analysis is called masking, designed to decorrelate the key-dependent computations from physical side channels. In particular, we talk about hardware implementations of masking schemes, such as, for example, threshold implementation or domain-oriented masking. Mathematical properties of these schemes vary to some extent, but the core concept is the following. Secure function f is split into n blocks, which we will refer to as shares following the TI terminology. What we call masking is the addition of uniform random masks, MI, to the inputs of each of the blocks. In case of Boolean masking schemes, which both of the mentioned ones are, the masking or this addition simply amounts to the XOR operation. Together, all of these n masked shares are a functional equivalent of f. One of their main advantages is that masking schemes are provably secure under certain sets of assumptions, abstracting the implementation of individual shares. On one end, this makes them suitable for both ASIC and FPGA implementations, and is one of the reasons why they are so popular. The exact sets of assumptions vary among different schemes, but the one assumption that is required for all of them is called the independence assumption. That is, that all shares leak information independently. In our case, this means that the supply currents of each shares are independent of one another. Now, from the electrical point of view, the independence assumption corresponds to shares being connected in parallel to an ideal voltage source with infinite current capacity. Therefore, the independence assumption is easily attainable for spherical shares in vacuum. In the real world, there appears something called out-of-model leakage. Thomas de Knude et al. Have recently demonstrated the existence of such leakage for a threshold implementation of a scheme on an FPGA board. They speculate that the culprits for this leakage may be either resistive IR drop across the supply rails or the coupling capacitances between the shares, or maybe both. Nevertheless, due to the proprietary internal structure and the complexity of FPGA devices, the evidence remains speculative. Therefore, to gain deeper insights into the sources of the so-called out-of-model leakage that is stemming from the layout parasitics, we conduct a more rigorous circuit-level investigation. This is the outline of the remainder of the talk, focusing on the experimental methodology and evaluation. And at this point, I would like to point out the following. The focus of is on the investigation from the circuit perspective. We do not argue whether this leakage can be exploited in practice, but simply try to uncover what might be its source should it exist. First, we introduce a more detailed model of the power distribution network, or PDN. This type of modeling is not new in the backend design community, but it has not been applied in the context of masking so far. In addition to the resistive voltage drop across the PDN rails, we account for the following. Firstly, the supply sag and ground bounce caused by the high-frequency supply currents or parasitic inductors in the PDN. In practice, these parasitics are significant at the level of bonding wires and vias, but to be thorough, we include them as well, and very soon we will see that they are indeed relevant for the security evaluations. Secondly, decapping capacitors are often used by the PDN designers to ensure the integrity of the power supply nodes, serving as a sort of charge caches for the fast switching logic. Given this PDN model, we use the sum of supply currents of each pairs as the side channels for diagnostic purposes. We perform all of our experiments using SPICE simulator of the fine seam suite from Synopsys. As the circuits we use are very small, we need to prevent the impact of ideal waveforms and numerical artifacts of simulations such that we can precisely isolate the core logic and observe the supply current of different shares independently. To do this, we buffer all the inputs, separating the ideal waveforms of, for instance, the digital vector file, and also introducing dedicated drivers for each share. Secondly, we use buffers from the target library, standard cell library, to create a more realistic voltage source. There will be more word about the sizing of these buffers later on, but we will see that even these buffers themselves can impact the SCA security. As the parasitic components are not chosen by the designers, it is difficult to predict the values without doing actual placement and routing. Instead, we manually annotate each of the parasitic elements, whether they belong to the PDN or to the coupling capacitances, and choose their sweep ranges as follows. So for each parasitic component, we start sweeping from the values that are negligibly small. Once they become too large, they cause the circuit to stop functioning. So these values are of no interest because these chips are never going to be made. On the other hand, designers try to meet the design constraints by limiting the parasitic components with the use of the EDA tools. Now, to account for all possible sets of constraints, so to speak, we choose the sweep ranges to be starting from the negligibly small values all the way up to the values that cause the circuit to malfunction. And at each point of the sweep, we perform the SCA evaluation to see how the level of leakage changes with the increase of the parasitic component. Again, the idea behind the experiments is to capture everything that can go wrong. On that note, as our circuits are very small, the values that you will see in the following slides are quite large, but necessary to cause significant perturbation in the power distribution network. Our experiments are largely automated using Python and Tcl scripts. So starting from a Verilog netlist and a set of parameters, for example, a number of traces or the sweep range, we generate all the finesim inputs, such as the top sweep file, the SPICE netlist of the design, as well as the custom parasitic annotations and the isolation circuitry that you saw in a couple of slides back. Then we run the SPICE transient simulation using the 10 picosecond step, generating simulated traces for each of the points of interest. So there's already going to be a lot of simulations. Next, we use custom parsers to validate the functionality and process the SCA data, moving then to the SCA evaluation. We base our security evaluation around the test vector leakage assessment, or TVLA. a widely used generic leakage detection test based on statistical moments. The first step of TVLA is to collect a number of traces, in this particular case supply current waveforms. Then we move to partition them in two sets based on the data associated to each of the traces. Then we compute the so-called t-trace obtained by performing the first order Balasch's t-test on the simulated traces sample-wise. What a test checks is whether the statistical moments of the two distributions for each sample are distinguishable. For the first order security, the moment in question is the mean. If a sample has a t-trace value above 4.5 in absolute, this means that the two distributions can be distinguished, and we say that the design leaks information. Now, as we do not care where does the leakage occur in the trace, but we want to observe the leakage trend in the function of different parameters, we simply use the absolute peak of the t-trace as the diagnostic metric. Due to the computational complexity of SPICE simulations and the large number of simulations that we need to generate each of the max T scores, each data point, we're limited to small circuit sizes. Nevertheless, as any Boolean function can be represented using XOR and AND gates in its algebraic normal form, we do not lose generality if we analyze these two gates. On the top, you see the trivial sharing of the XOR gate into two shares, while the threshold implementations of the N2 gate requires a little bit more gates, having 3 shares and also consuming an extra random bit R. With all this in place, we move to discuss the experimental findings, starting from the impacts of the power distribution network. We use the 8-bit wide instance of the first order secure 2-share implementation of the XOR gate. As the single bit XOR has only 4 input bits, shared version of it that is, we use the 8-bit version to increase the input space and to increase the current drawn from the supply. Notice that since the circuit is linear and the sharing is completely symmetrical, any leakage that appears must stem from the power distribution network, and in that sense this is a very convenient circuit for this study. On the left hand side we see the mean drop in the power supply nodes VDDI for different sizes of the supply buffers. Note that we remove all other parasitic elements from the circuit for this experiment. For the ideal voltage source, depicted in the black line, we see that the max T score remains very low with the increasing number of traces as we expect. So on the right hand side, we see how this max T point moves with the increase of the traces, and that's stable. On the other hand, as we start decreasing the driving power of the supply buffers, by adding, so from infinite to buffer x32 to buffer x8, etc., we see that the supply rails start dropping and the levels of leakage are starting to rise with the increase of the number of traces. Here also note that should we increase the total number of traces, these trends would only continue and we would get more extreme results. For the smallest buffer, the circuit malfunctions, so the trace on the right hand side, although present, isn't really relevant because again this circuit would never be made. But on the other hand, we see that the red and the green and blue trace corresponding to the x32 and x8 buffers, they result in an acceptable 10 to 15% voltage drop in the power supply, while increasing the leakage quite significantly. So everything else being ideal and everything else being equal, we see that simply these nonlinearities in the supply can impact the level of leakage. Henceforth, we will be using this buffer x32 as the reference parasitic-free case in our experiments. Next, we look at the impact of decoupling capacitors between the supply rails and the ground on the left-hand side, as well as the capacitors additionally annotated between the supply nodes on the right-hand side. As there are several capacitors and many different values swept, we overlap different cases for simplicity. Green color is used to represent the reference case, while the black colors represent the max-T scores for different values of parasitic components. When the circuit malfunctions, the traces are plotted in gray. As the name may suggest, the decoupling capacitors help the SCA security by effectively filtering the information carrying high-frequency supply current. Therefore, we see already at this point how back-end design techniques could be used to provide an additional security margin. So far so good, right? So these decoupling capacitors may actually help. Now, looking at one of the original suspects, the parasitic resistors of the power distribution network. On the left-hand side, we see the evolution of the max-T scores for the parasitic resistors of the share 1 PDN. Increasing resistors up until the 10 kOhm, we see only a slight increase in the levels of leakage depicted in black lines before the circuit stops functioning correctly, shown in gray lines when simply the results don't make sense and statistics shows lower levels of leakage. On the right-hand side, we see the same plot, but for the parasitic resistors of the share 2 PDN, as they're affected only by the supply current of the second share. Increasing them attenuates the side channel signal, lowering the overall amount of leakage. Now here we see that the original assumption about the impact of the resistive drop does not seem to hold. Unlike the resistance impedances from the previous slide, parasitic inductors have a significantly more dramatic impact. We see that sweeping parasitic inductors of the share 1 PDN drives the max-T score outside of the confidence interval with only 32K traces, meaning that this impact is actually very significant. Compared to the RP1 and RG1 from the previous slide, so the parasitics resistances in the share 1 PDN, the impedances LP1 and LG1 are dependent on the frequency of the inciting current. Therefore, there is some sort of a nonlinear mixing of the supply currents of the share 1 and share 2 over these inductors, causing the voltage drop that in a way couples the two shares. Now, in practice, existence of significant parasitic inductors in the logic core would very quickly lead to an oscillatory behavior, quickly obliterating the circuit functionality. Nevertheless, looking at the position of LP1 and LG1, these parasitic inductors may well belong to the bonding wires outside the chip. Therefore, this is not entirely irrelevant, or it is possibly dangerous in practice. And how relevant it is, we can discuss by looking at the values. I mean, here we show the max-T score depending on the value of the parasitic inductors. X's denote the moments when the circuits start malfunctioning or stop operating properly. Now, these values are unrealistically large, especially if you assume that they stem from the logic core itself. Nevertheless, remember that our target circuits requires orders of magnitude smaller currents than a full design. Therefore, the critical inductances could fall below the ones needed to meet the design constraints in a real design. Again, we're just trying to see what could go wrong. In our opinion, this shows that layout phenomena need to be taken into account when doing pre-silicon evaluations. Lastly, we move to investigate the impact of coupling capacitors, previously the main suspect for the out-of-model leakage. To inspect the impact of coupling capacitors in detail, we annotate capacitors between each pair of nodes. For a circuit of n nodes, this amounts to n choose 2 total capacitors, making the experiments rather time-consuming. We distinguish 4 groups of nodes. Firstly, the cross-data capacitors coupling data nodes of 2 different shares. Secondly, the shared data capacitors coupling data nodes of the same share. Share rail coupling data and the rail of the same share, and then the cross rail coupling data nodes from one share to the rail node of the other share. And then according to theory, only the cross data and cross rail shares may lead to leakage. And indeed, our experiments remain in line with the theory. So targeting the single bit XOR gate, we see that only the cross-data capacitors may lead to significant increase in the levels of leakage. Interestingly, the cross-rail ones do not show any significant increase. Looking at the right-hand side plot, it seems that the leakage induced by the cross-data capacitors is similar to the ones caused by the parasitic inductors in the previous case. But if we take a closer look at the corresponding values of the cross-data capacitors, we see that the high levels of leakage appear for the values that are in the tens of femtofarads. Now, contrary to the arbitrarily chosen PDN parasitics, we believe that it stands to reason that parasitic capacitors are of the same order of magnitude as the input pin capacitances of the standard cells from the target library. And looking at this library documentation, we find pin capacitances to be at the order of several femtofarads. Therefore, we find the values of tens of femtofarads to be rather unlikely, and therefore we find that the risk of coupling capacitances causing this out-of-model leakage may be lower than previously. We then repeat the experiments for the 3-share threshold implementation of the N2 gate, focusing on the many cross-data capacitances that it has. While other observations hold, we add one more consideration. Apart from the levels of leakage being slightly lower than for the small XOR gate, we also split the capacitances into 3 risk groups, calling them high, medium, and low. We draw the lines between the groups somewhat arbitrarily, but the main message is the following. Even if certain capacitances lead to higher levels of leakage at the high end, looking at the blue traces, they drive the max t-score out of the 4.5 range much later for values around 10 femtofarads. We deem these capacitors to have a lower risk of leaking information than the one plotted in black, as they are simply much more likely to occur in the design. With this, we conclude our investigation, concluding the following. We provide additional insights into the out-of-model leakage of masking schemes. To do so, we introduce a more detailed PDN model and propose the co-simulation of the PDN along with the logic core. We show how different parasitic components affect the first-order security of masking schemes. And to me personally, it seems that previously suspected coupling capacitors have less alarming impact than the power distribution network. Therefore, we continue our work in 2 directions. So primarily we further investigate the effects of the power distribution network, and we're starting to see how can we scale up this approach. For instance, back annotating traces from digital gate level simulators such as Primetime or some other simulator back into the analog model of the PDN in order to be able to analyze larger designs. There's a lot of work to be done, but we hope that this new view of the out-of-model leakage and the method of analysis serves as a guide for digital designers, a guide to which parasitic elements matter for the SCA security. At this moment, normally I would invite you to ask questions, but since this is a virtual conference, I invite you to look at the paper and contact me in any way you can, and I will happily answer all of your questions. Thank you.